Well, good evening, ladies and gentlemen. I think it's time to start the evening's program. My name is Paul Davies. I'm director of the Beyond Center for Fundamental Concepts in Science, popularly known as the Center for Cool Stuff. And once a year, we put on a lecture to honor the memory of Eugene Shoemaker, who pioneered the science of asteroid and comet impacts. He worked for many years in Arizona and was much admired and loved by his colleagues. Hence this lecture. This evening's lecturer is Dr. David Grinspoon, but before I introduce him, it's my pleasure to welcome Cynthia Heath-Smith, who's sitting in the front row here, Gene Shoemaker's niece, and she's graciously agreed to say a few words about her famous uncle. So, Cynthia.
Thank you, Paul. Well, thank you for giving me the opportunity to say a few words about my Uncle Gene. My mother, Maxine Shoemaker Heath, is Gene's younger sister and his only sibling. Gene was an inspiration to my parents, who pursued academic careers in the biological sciences, and to me. His love of science was infectious. Spend just a few minutes with him and you were hooked. My childhood aspiration to be an astronomer was motivated by him, and when I instead later turned to archaeology, that decision too was inspired by Gene. He had a great interest in and respect for the indigenous peoples of the southwestern US, and his and Carolyn's wedding gift to my parents were two Gray Hills Navajo rugs. Their gift to Mike and me was a Navajo wedding basket. Gene's legacy had a lasting impact, if you will, on our understanding of planetary geology. Last year on a visit to Germany, I told my husband Mike, there was one place above all that I wanted to see, the Nordlinger Ries crater. He gave me a puzzled look, and I explained, well, I'd heard my uncle talk about the crater and the town's medieval church built of Sweevite, which is a rock formed by impact. I looked up the address for the Craters Museum in Nordlingen, and imagine my surprise to find that it is located on Eugene Shoemaker plots. If you ever have a chance to visit there, the museum is fascinating, the staff are welcoming, and it is a fitting tribute to Gene and his many contributions to our understanding of our own planet's geology. Thank you.
Thank you so much, Cynthia. It's always great to get somebody to introduce the proceedings who actually knew Gene, and to be related is one better, and so you're very welcome. So let me move on then to introduce tonight's Shoemaker lecturer. This is David Grinspoon. He's senior scientist at the Planetary Science Institute and longtime advisor to both NASA and the European Space Agency on space exploration matters. He held the dream job of Congress chair in, Library of Congress chair in astrobiology. And that meant he got to read any book he wanted. But he was not idle during that time. Not only was he reading books, he was writing books. And one of these, it's called Earth in Human Hands, you will have noticed is for sale this evening outside the auditorium. And David, if you speak to him nicely, I'm sure will sign your copy for you. So that will be after the proceedings. I should mention that if you're sufficiently inspired by what he has to say this evening on the subject of planetary intelligence, and I'm not sure I know what that is, but we're going to find out, then we have a whole day symposium tomorrow, and you're very free to come and go as you wish. We have a distinguished lineup of interstate visitors who will be addressing the theme basically of the destiny of mankind. So we should have it all figured out by the end of tomorrow afternoon. Please do come along. Details you can find on flyers outside if you didn't take a note from the screen a little bit earlier. There will also be a webcast of the proceedings. that is all I have to say, except switch off your cell phones. And without further ado, I would like to ask Dr. David Grinspoon to deliver the 2018 Eugene Shoemaker Memorial Lecture. Thank you.
Thank you. All right, thank you so much, Paul, and thank you all for coming out tonight. It's a pleasure to be here, and it's it's really an honor for me to be invited to give this lecture, in particular because Eugene Shoemaker is someone who was a great inspiration for me, and indeed for everyone in my field of planetary science. He was the father of planetary geology, which is part of the mix of planetary science. It's the part where we apply principles of Earth geology to understanding other planets, and also, in turn, learn more about the Earth from the comparisons we make with other planets. And Eugene Shoemaker really, more than anyone else, brought geology into planetary science. And here he is, as I actually got to know him. I was very fortunate when I went to grad school here in Arizona, not at this wonderful institution, but as the school you probably think of as the lesser institution down the street in Tucson. I got my PhD in Tucson, and I was there in the 1980s and had the amazing pleasure of going to Meteor Crater with Eugene Shoemaker, who is the person who figured out that Meteor Crater is a meteor crater. His PhD project, when he was a geology grad student at Princeton, was he did his field work here in northern geology at Meteor Crater, and he's the one that proved beyond a doubt that it really was the result of an impact crater from an object striking the Earth at high velocity and blasting out this crater. And that was so much of the key that unlocked a lot of our connection with the rest of the solar system, because once you realize that when you look at the moon, all those craters there are the result of the same process that we can observe the effects of here on Earth. And it was part of this project of connecting our existence here on Earth with the rest of the solar system. And Eugene Shoemaker's insight in Meteor Crater was absolutely key. He was also, and here he is along with his wife, Carolyn, he was also a fantastic telescopic observer. And that combination of being a geologist and an astronomer is really the brew that makes up planetary geology. And Gene was expert and made very important contributions in both areas. He figured out the telltale signs that can prove that a crater really was formed by a high-velocity impact from space. Before then, people had thought, well, maybe Meteor Crater is a crater like the craters on the moon, and maybe they're all formed by high-velocity impacts. But it could be some kind of volcanic feature. Maybe it was formed from some big steam explosion underground. There were other theories. But Gene, through his meticulous fieldwork and theory, showed that there were features, and here, of course, is beautiful Meteor Crater, features like these overturned beds on the rim. In other words, when the crater hits, it blasts out this material. So this layered bedding that you're very familiar with here in northern Arizona, parts of it get peeled back, literally like the sheet on a bed, folding over. So you can see the sequence goes backwards. You've got this Kaibab formation, which is, these are limestones formed in the Permian, I believe. If I say something wrong, my geology friends are gonna, well, anyways, they'll rib me later. And then the Moenkopi formation. These are well known if you go to the Grand Canyon or any of these places in Arizona where these the rocks, the layers of rock are exposed. You see the same formation, but then they reverse themselves. So you've got Moenkopi on top of Kaibab, which is normal, but then it flips over, and it goes back, and you've got Moenkopi with Kaibab on top of it. These overturned beds, that was part of, Gene showed both in the theory and in the field work, that that's really a unique sign, and there are many other signs as well, but showing that this really is an impact crater. And that was the key that unlocked so much of our connection with the rest of the universe. I mentioned he was also a telescopic observer. During the time when I was a grad student here in Arizona in the 1980s, large impact events were all the rage. The notion that Earth could be hit and Earth's history had been affected by large objects from space occasionally hitting the planet. In I think it was 1980 or 1981, the very important paper was published by Alvarez et al., showing that the event that wiped out the dinosaurs, and not just the dinosaurs, but most of the species alive at Earth on that time, the Great Mass Extinction 65 million years ago, was they showed very convincing evidence that that was caused by an impact from space. And then that sort of opened the floodgates to a lot of new theory about how these catastrophic events had affected Earth history. So large impacts were all the rage, and this is an artist's depiction of that event. And then the crater was found, sort of the smoking gun, down in, it's called Chicxulub crater off the Yucatan Peninsula in Mexico. So now we know that the history of Earth has been affected by these occasional, really powerful, catastrophic impacts from space. And among other things, this got some people to start thinking about the fact that if this has happened in the past, it can happen in the future, and starting to map out the population of objects in our solar system, asteroids, mostly some comets, that can hit the Earth. And Eugene Shoemaker was seminal in that effort to get that mapping going. And in fact, he and Carolyn as a team discovered many of these near-Earth objects. And in fact, in, I believe it was 1993, Gene and Carolyn, along with David Levy, discovered this, Shoemaker-Levy 9, named after the discoverers. And this is an extraordinary object that led to an extraordinary event. What you're seeing here is a comet that has been ripped apart by making a close approach to Jupiter. The tidal forces from coming close to Jupiter ripped this apart into a sort of string of pearls of smaller cometary objects. And when they discovered this, they projected its path into the future, and they were able to predict that, strangely and remarkably, this object was going to hit Jupiter. The string of objects was going to hit Jupiter in July 1994. So Shoemaker-Levy 9 was an amazing discovery because it allowed us to predict and observe a large impact event on another planet, which allowed us to learn a lot more about what really happens when you have these high-velocity impacts. And that was really quite something. Up here in the upper left, you can see a little movie of infrared images. That's Jupiter. That's Jupiter's moon, Io. But down here, this flash that grows and then disappears, that's actually a series of infrared images of one of those fragments of Shoemaker-Levy 9 striking Jupiter. And this is the view that I was fortunate to see through a telescope in Colorado, where I was at that time with some friends at an observatory up there. We actually, there's a teaching telescope, and we actually put the eyepiece on it, and we're able to actually look through the telescope and see this extraordinary sight of Jupiter with these new blemishes, which is not something you see every day. And the reason why there's a line of them is because as Jupiter goes through its 10-hour rotation, every couple of hours it was being hit by one of these other fragments of Shoemaker-Levy 9, which was making a big explosion, and there's all this dark soot and material that formed out of the explosion that made these stains that lasted a few days and then disappeared. So that was really something, and we were able to make predictions and then confirm a lot of ideas and theories and get a little bit smarter about what really happens when objects hit the Earth. And out of all this has become an awareness that Earth is not isolated. We knew this in an abstract sense, but we know it. We know so much more about it now than we did, half a century earlier. That what this plot shows This is, sorry to be a little nerdy here. I know some of you love it and some of you are like, what? But this is a log-log plot, meaning each one of these tick marks is, so that's 1, 10, 100. And this is megatons of energy. So the ones down on this side, these are larger impact events. And this is how often these objects hit. So the little ones that are only, 1 megaton or so, hit roughly once a century, and that's Tunguska was this object you probably heard of that hit the Siberian forest and flattened trees for hundreds of miles. And those, that's, as far as impacts go, that's not that powerful event. Here's Meteor Crater, which is roughly once in a millennium or a little bit longer. It actually hit about 50,000 years ago, and it shows you, it's roughly a 10 megaton TNT equivalent. And then there are the really large ones, and this is that KT impactor. This is that object that did in the dinosaurs and so many other species 65 million years ago. And those kinds of objects hit Earth on average maybe once every 100 million years, and they're absolutely every 100 million years, and they're absolutely huge and catastrophic. So this is the worry, or the realization that this can happen, will happen again, ultimately, if we wait long enough, if we don't do something about it. But of course, unlike the dinosaurs, we do have a space program, and we have this realization now and the potential to do something about it. But the other point I wanted to make here, and I'll come back to this, is that this realization that there's the spectrum of impact events from things the size of Meteor Crater that hit, maybe once or so in the time that we've had human civilization, the kind of human civilization that keeps written records the last 10,000 years or so. Actually, that was 50,000 years ago, but roughly speaking, this is a 10 millennium event. So there, it's possible that there are some of these in living memory of human civilizations, and there are some interesting questions of whether some historical events that are recorded are actually observations of impacts of this size. But then there are much larger events that happen. There have only been modern humans for less than 1 million years. So chances are these events have never happened when there have been human beings on Earth. And so we've become aware of this spectrum of events that can affect our planet, that are completely outside the realm not only of your personal experience and my personal experience, but the experience of our species. And yet they're very important in determining the course of our planet. So this gave a new wrinkle to some ideas, some sort of quasi-philosophical ideas in geology. Geologists were fond of saying, still are fond of saying, the present is the key to the past, meaning that you can understand everything in Earth history if you look at the present-day processes and the rates of those processes, and you extrapolate them over huge amounts of time. And there was this sort of tension between ideas that we used to call catastrophic and uniformitarian. Catastrophic ideas were, a long time ago, associated with sort of biblical changes. Like the only way you could explain these giant mountains and these big basins were because of vast floods of biblical proportions. And then it was a big revelation in the 19th century that geologists realized how deep time was. And that was where this notion that the present is the key to the past. And catastrophism was sort of discounted in favor of uniformitarianism, which seemed more modern and scientific, and you didn't need these catastrophic events to explain things. You could explain everything happening on Earth by studying current processes and extrapolating back in time. But with this realization that there were these huge impact events completely outside the experience of our species that had, in fact, had a major effect in determining the evolution of our planet and the evolution of life, there was sort of this resurgence of what sometimes people called the new catastrophism. This realization that, the present is the key to the past, but there are processes that have never been observed in the present, which are completely important in determining the nature of our planet and the course of our planet's evolution. So this connection to deep time and the connection between processes happening on Earth and processes happening elsewhere in the solar system is really what I think of as the greatest legacy of Eugene Shoemaker. And before I move on, I also just want to say one other thing about Gene, which is that he was an extraordinarily nice guy. I thought of him, as a lot of my contemporaries did, as this sort of god of planetary science, because he was one of the people involved in all these missions like Voyager and so forth. And when we were students coming up, you know, these were the people that just seemed larger than life. And then when I first met him, he was so nice, and he was the kind of guy that would just give all the time in the world to a young student and acknowledge your ideas and make you feel like your ideas were worth pursuing and worth expressing. And when you meet somebody who's that significant in his own work and yet that kind to young researchers, it's really a wonderful combination. So I really appreciate Gene and everything he did. Anyways, so I got involved in this particular topic Paul mentioned, but I had this extraordinary opportunity in 2012, 2013. I became the first holder of what is now a regularly rotating position, the chair of astrobiology at the Library of Congress. And when I saw this ad, they were particularly looking for people to do research at the intersection between astrobiology and its societal implications. Astrobiology is the study of the potential for life elsewhere in the universe. And we use the record of life on Earth and our growing knowledge of environments elsewhere to try to understand where there's potential for life elsewhere and how we might be able to find it. And so astrobiology is something I've been pursuing for a long time, but the idea to spend a year pursuing a different angle in astrobiology that was connected to the humanities was a wonderful enticing opportunity. So I wrote a proposal. This was the title of my proposal, Astrobiology in the Anthropocene Era, exploring the roles of life and intelligence on Earth and beyond. And the Anthropocene is the word, if you haven't heard it, is the idea that we have entered a new geological epoch that is determined by the presence of the actions of humanity as a new geological force on the planet. And it's been a sort of controversial but very fruitful idea. And I wanted to explore that from an astrobiology angle. And indeed, I was very fortunate to be selected as the inaugural chair of astrobiology. And I went to the Library of Congress for a year and worked on this. And out of that came this book, Earth in Human Hands, that I'll now share a few ideas from. In a way, the goal of astrobiology is to figure out where we fit in to what we sometimes call cosmic evolution. Cosmic evolution is the entire story of the universe with a focus on the transition points, the major changes that the universe has gone through, the stages, if you will. And this is my one-page cartoon of all of a cosmic evolution. And so it's a big story to fit on one page. The compression ratio is rather high. But you can see some of the highlights here. There was the Big Bang, which you've heard about, and galaxy formation. And within galaxies, you had molecular clouds, which made stars. And around stars, planets formed. And on the surface of some planets, some weird chemistry, which allowed life to form. And then on at least one planet, we had the evolution of what we call complex life and what we so proudly think of as civilization. And then this ends with question marks. What's next? Why should we think that this stage is the apotheosis of cosmic evolution? There's no good reason, really, to think that. And by the way, inside the magnifying glasses here, you can see what's happening on the microscopic scale. So you get elements being formed inside of stars, and you get simple organics being formed in the clouds around young stars, and you get more complex molecules being formed on the surface of planets. Another thing to notice here is that everything on the left side of this cartoon, these are all processes that we now know to be universal. They happen everywhere in the universe. Galaxies, stars happen everywhere. And everything on the right side represent phenomena that for a long time we've wondered if they're universal. And the amazing news, of course, of the late 20th and early 21st century is that now we know that planets are, in fact, part of this universal sequence. With the discovery of the exoplanets, which is still recent and ongoing and a remarkable revolution in knowledge of our time, we've learned that, in fact, as we suspected, planets are everywhere, around basically every star in the sky. So this box has moved from the category of, we know it happened here, we suspect it might be universal, to we know it's universal. And in a way, with what we're trying to do with astrobiology is do the same thing with this box and this box. Can we, in the same way that we did with planet formation, find evidence that the origin of life and even the evolution of complex life are not phenomena that just happened here, but in fact, are they universal? We suspect they are. I would say a lot of scientists believe they are. Whether that belief is based on evidence is an interesting question we can come back to. But at any rate, so that's astrobiology, and the question is, one question is, what can we say about this stage, the evolution of complex life, in sort of a generalized sense, in a way that might actually even be helpful to us as we negotiate some of the challenges of our time? I mentioned the Anthropocene. I won't dwell on this, but there's a lot of data that goes into this claim that there's a new geological force on Earth. These are various compilations of data showing various human interference into the Earth system, and whether you look at population or the damming of rivers or urban population or McDonald's restaurants, you can see there's a certain similarity in the form of all these, and they all kind of kick along until the mid-20th century, and then there's a sharp uptick in a lot of these. And that sharp uptick that really begins in the 1950s is what we call the Great Acceleration. And then this next slide shows these are all effects on the Earth system that come out of those human interferences. So things like ozone depletion and obviously CO2 concentration, the changes in biodiversity, all of this contributes to this, I think, pretty solid claim that we are in a new geological time on Earth forced by the actions of human beings. Now, how does that fit into the big picture, the overall history of Earth? The Anthropocene has been proposed as a new epoch here, following the Holocene. And you've seen this before, this geologic time scale on the walls of classrooms or wherever. And we split it into these different kinds of time periods. And the epochs are kind of the small ones over on the right here. They last for maybe a few million years. So the Anthropocene, as I mentioned, has been proposed as an epoch. But I have been thinking, and I write about this in my book, and I'll give you briefly tonight some of my reasoning for this, that it might be something much more significant for that, that maybe we've entered a new eon. Now, eons are the big divisions of time on the left of this chart. And there have only been 4 eons in Earth history. And while the epochs are very significant to us and other species, because a lot of the boundaries represent mass extinctions and so forth, from an astrobiological point of view, these are just kind of fluctuations. You're not going to find a Pliocene or a Holocene on another planet. They're just random fluctuations of Earth history. But I would claim that the eons are of more significance to astrobiology in that these are divisions of time that we may actually be able to observe on other planets. Not the exact same history, but each one of these represents a different phase of Earth when Earth was a fundamentally different planet. And in fact, each one represents a time when there was a fundamentally different relationship between life and the planet. And these boundaries are changes in that relationship. So there's a lot of different ways to describe this, but basically the Hadean, as the name implies, that was hell. And that was when it was all large impacts constantly, and steam and lava, and you couldn't really have anything living on the planet. More or less the boundary between the Hadean and the Archean, which was about 4 billion years ago, this is roughly the origin of life. So that's why I say this is a transition in the relationship between life and the planet. And then the boundary between the Archean and the Proterozoic eon, again, this is, there's a lot of different ways to describe this, but in a sense, this is when life took over the planet. We talk about the great oxygenation event, when the oxygen rose in the atmosphere of the planet due to the influence of life, and life sort of took over the planet chemically. And then this boundary between the Proterozoic and the Phanerozoic, this was when life got large, when life became macroscopic, the origin of animals and plants and more complex, large-scale life that leaves fossils. And so each of these boundaries is significant. There's a significant change in the planet, change in the relationship between the planet and life. And I would submit, and I'll argue for this for the next half hour or so, that this could be regarded now as a new eon transition, because I think arguably what we're seeing now is the advent of cognitive processes as a geologic force. You can ask, what's really new about the Anthropocene? Is it just it's just another species? Why are we so self-aggrandizing as to name a geological epoch after ourselves? But maybe there's actually a really fundamentally different kind of process going on here. And I think there is, and I think what it is the integration of cognitive processes into the evolution of the planet. Now, of course, for it to actually be an eon, it has to last for an awful long time. And nobody knows if the Anthropocene is just going to be a flash in the pan because we can't keep our act together, or if it's actually going to. So in a certain sense, this is an aspirational title. But unlike Anthropocene, it doesn't have humans, it doesn't have anthro in the title. So this is, to me, is something a little bit more abstract. The idea that a planet can have a Sapiezoic, that cognitive processes are a fundamentally different way of life interacting with its environment, and that if cognitive processes become a long-lived component of a global system, which you can argue is something that is one way to look at our struggle now for sustainability, that if that can become sustainable and long-lived, then a planet would have a Sapiezoic. Whether our planet will, whether we will be part of that, it's a concept one can discuss, especially when one realizes that there are lots of planets, presumably with life evolving, and this is something that may happen elsewhere, even if it doesn't happen here. So anyways, backing up now, the local part of our story began about 4.5 billion years ago with the formation of the planets through a process that we call accretion. Accretion is the gathering together of smaller bits of planet stuff into larger bits of planet stuff through collisions that become more and more energetic and more violent as the protoplanets get larger and start to tug on each other with increasing gravitational force. And then at the end of this accretionary process, there are a few planets left standing, and that is what that end of that scrum, the bumper cars of activity that happened pretty fast. It happened in probably just a few tens of millions of years. We went from a nebula of gas and dust to planets. At the end of that was the origin of the Earth and its sibling planets. And then a lot happened, and I've only got an hour, so I'm going to fast forward through some of that. But imagine you were a very patient alien astrobiologist watching the evolution of the Earth through these last 4.5 billion years. What would you observe? Well, you'd see a lot changing. You'd see the continents shifting around over time. Imagine a time-lapse view of the Earth, morphing, coalescing together and splitting apart as in this sort of spherical jigsaw puzzle of continental drift. You'd see ice ages and hothouse climates coming and going, so you see the polar caps growing and shrinking over time in this sort of semi-rhythmic pattern as the climate changed. About 500 million years ago, or 400 million years ago, you'd see the greening of the continents, which when life finally colonized the land and the atmosphere became oxygenized, and we had green plants and forests. But throughout all that time, the night side would have been a nearly unbroken black. You would have the occasional flash of aurora or flash of lightning. And then after that 400 million years, you'd have the occasional forest fire, but it would mostly be an unbroken black until very recently. Whoa, what's that? The night side starts to light up in these patterns that start in a few coastal areas and these sort of nodal patterns that spread throughout the continents and join together. A very recent change, and along with that recent change, you'd see a host of other changes happening to the planet. The changes in the atmospheric composition, changes in the geometric patterns of the land itself, and then these strange linear wave patterns moving across the ocean and strange linear clouds streaking through the sky, changes in the ocean composition. All of this happening very rapidly. And then very recently, in the last blink of an eye, geologically, in the last 60 or 70 years, you'd see something even stranger, perhaps. Little bits of the planet, after 4.5 billion years after it all accreted, falling through gravity, now all of a sudden you see little bits of the planet launching themselves back out into space. Little metallic insect-shaped objects moving off the planet back into space. And that would be a very strange thing to behold. It's what I call the curious anti-accretion. And I mean curious in two senses. It's a weird thing for a planet to do, and it's also the hallmark of a certain kind of curiosity, technologically enabled curiosity, appearing on Earth. And with that technologically enabled curiosity, one species has been sending little robot emissaries elsewhere throughout the solar system and sending radio signals home again to try to make some sense of our surroundings and try to piece together our origin story. Now, through those efforts of exploring the planets, we've learned a few things that help us get some perspective on ourselves. Through this effort of comparative planetology, which really Eugene Shoemaker helped us get started, and which a lot of us are doing our best to continue. We look for similarities and differences among the stories of the planets and try to learn some general principles of how planets work and how our Earth fits in with the rest of the universe. One thing we've learned, especially when we do this comparison of Venus, Earth, and Mars, our nearest rocky neighbors with atmospheres, is that it seems as though these planets had very similar origins in early environments. The more we study the early history of Mars, the more we realize that at the very beginning it was an Earth-like place with a more moderate climate and running water. And we have not explored Venus as fully as we have Mars. And if you want to get me riled up, you can ask me about that and why I think that is and whether I think we should be exploring Venus more, but I'll try not to get on my soapbox now. But what we can piece together from the exploration we have done suggests that Venus also, when it was young, was a much more Earth-like place with liquid water, oceans, and a more moderate climate. So it may be that all three of these planets had the conditions for the origin of life. In fact, it may be that rocky planets in the universe often, maybe even usually, start out with the right conditions for an origin of life. And that what's rare in Earth's story is not those early conditions, but maintaining those conditions over all these billions of years. And whether life itself has been instrumental in helping to maintain those conditions is a really interesting question. But at any rate, it seems as though these planets had similar origins in early environments, and then they went down different paths. And for whatever reason, and we think we know some of the reasons, and we're still trying to understand, Earth went down this path of becoming flagrantly inhabited by life, to the point where it's not really accurate to simply say that life happened on a non-living Earth. In some important sense, it's more accurate to say that the Earth came alive. Because the more we understand about the role of life on Earth, it's not just skin deep. It affects all of these great biogeochemical cycles. There is 2/3 of the minerals on Earth are biogenic. Obviously, the atmosphere, all this oxygen we're breathing is a product of life. And the more we study the role of life on Earth, the more we understand it's really pervasive. And my colleague, Colin Goldblatt, said it this way at a recent meeting. He said, the defining characteristic of Earth is planetary scale life. And Earth teaches us that habitability and inhabitants are inseparable. So it's not merely the case that life is something that happened on Earth. To an important degree, life is something that happened to Earth. Life is, and maybe this is always true, that life is something a planet becomes, rather than sort of an afterthought on a non-living planet. At any rate, Earth went down a different path than the neighboring planets. And more recently, Earth has been under the influence of this new type of geological force, leading to what we call the Anthropocene. And this history makes me wonder, could intelligence, like life, become a planetary property? Not just something that's happening on a planet, but something that becomes integrated into the workings of a planet. And in a way that this is a teaser for this symposium we're going to have tomorrow on planetary intelligence, where many people are going to give their perspective on versions of this question. And I'll come back to that question, but I want to point out now that when we're thinking about what it is about humans that's really unprecedented in the history of the planet, it's certainly not true that we're the first species to come along and radically change the planet. And it's certainly not true that we're the first species to come along and wipe out other life forms and cause mass extinction. It's not even true that we're the first species to come along pursuing a new energy source and flagrantly polluting the planet. Because in fact, 2.5 billion years ago, these little guys, the cyanobacteria, did all that. They look innocent enough, don't they? But in fact, in reckless pursuit of a new energy source, they polluted the atmosphere and wiped out many, many other species. Now, in their case, that new energy source was solar energy, because these guys perfected photosynthesis, and that polluting gas that they so recklessly put into the atmosphere was O2, oxygen. And oxygen is highly destructive of organic molecules, the stuff of life, the stuff that we're made out of. Oxygen reacts violently with organic molecules. So that was really bad news for the species that were on Earth at that time. Now, as often happens in the evolution of life, there's an opportunism where a catastrophe becomes an opportunity for some other life form. And the fact that those oxygen molecules react so powerfully with organic matter became something that could be exploited by future life forms once they perfected what's known as respiration. That's how we live. Those powerful reactions of oxygen and organic matter, that's how we power ourselves. But before life evolved that capability, this was a disaster. In fact, Lynn Margulis, the founder of the Gaia hypothesis, in one of her papers, she referred to this as the oxygen holocaust. So anyways, we are not the first species to cause global change, but yet there's something different about us. So what have we got that the cyanobacteria didn't? And this gets into these fraught debates about human qualities. You can talk about language, tool use, art, technology. There's whole literature about human exceptionalism. All of these are arguable and controversial. You can talk about intelligence, consciousness, foresight, awareness, cumulative knowledge, responsibility. I was given a version of this talk at the SETI Institute, and my friend Jeff Moore made the comment that this is a list of all of the qualities that we don't have enough of, which is a fair point. But nonetheless, even though we can argue about any one of these, I think the ensemble, we can talk about human qualities and admit there's no other species on Earth that has this ensemble. There's something new and unique going on here. But we can also ask, are these qualities adaptive, or are they an evolutionary dead end? Looking at our current situation on Earth, you might draw either conclusion. Could they be a potential gateway to great longevity? If civilization is now a geological process, what are its prospects both here and elsewhere in the universe? In order to get a handle on this question, I've put together a sort of taxonomy of planetary changes categorized with respect to the role of life. So what I call planetary changes of the first kind, those are just random catastrophes where life has nothing to do with it. Life is just in the wrong place at the wrong time. An asteroid hits the Earth. That's the canonical example. But there are other examples. A big outpouring of volcanism from inside the planet because of some burp in the interior convection of the Earth causes a mass extinction. These are, life is not implicated. It's just, this is, when bad things happen to good planets. But what I call planetary changes of the second kind, these are biological catastrophes. And I gave the example of the evolution of photosynthesis and how these are just catastrophes that happen when a species is doing its thing, multiplying, finding new ways to live, and as a consequence, that species changes the environment in such a way that's harmful to other species. And the green leaf symbolizes that oxygen catastrophe. There are other examples of biological catastrophes in Earth history, but that's sort of the obvious best one. And then we get to the point where the cognitive processes enter into the story. And I would submit there are two very different kinds of planetary changes, both of which involve cognitive processes. And I think the distinction between the two is very important. The first is what I call planetary changes of the third kind, or inadvertent catastrophes, symbolized here by traffic. So each of these cars is driven by somebody with agency. We're pretty good at navigating around obstacles, hitting the brakes, hitting the accelerator, steering. We can drive, and each driver has agency, but yet you can still ask the question, who is driving the global transportation system? And the answer really is kind of nobody. So there are these processes that we're participating in, but don't really have any sense of active control over. That's what I mean by inadvertent changes. So this is what happens when a very clever species develops the ability to use technology to solve local survival problems, and gets so good at it that they spread themselves around the planet in such a way that at first, completely unbeknownst to themselves, they start causing global changes. And these are what I mean. That's what I mean by an inadvertent catastrophe. And that leads to, let's sort of cut off here, but what I call the Anthropocene dilemma, which is when you have when your actions have global consequences, but you don't have any global control. And whenever your domain of action exceeds your domain of awareness and control, that's an unstable situation. You can liken it to a child that doesn't have what we call situational awareness. So they'll, a kid with a big backpack will walk into a store and turn around and smash things off the shelf because they're not aware of the scope of their influence. And if you want, you could even look at it in terms of system theory that positive feedbacks are more likely than negative feedbacks when an agent is acting in a domain that exceeds the domain in which it is aware or sensing its surroundings. So at any rate, that's what I mean by inadvertent changes. And of course, the examples are obvious, and I won't dwell on them here because I don't want to talk too long. But you know about the Keeling curve and the rise of carbon dioxide and all the scary effects, the decline of sea ice and so forth. This is the most obvious example of an inadvertent change. It's inadvertent because when we started burning fossil fuels, we didn't say, hey, let's change the climate. We said, hey, this is a good energy source, and it was. But unintended consequences. Another example of this, of course, is the famous ozone hole, which was discovered, by the way, in part because we were studying the planet Venus, and some scientists were trying to figure out what was up with the missing oxygen compounds in the upper atmosphere of Venus. And they realized that it could be chlorine, that chlorine catalytically destroys ozone and other oxygen compounds. And then some other scientists read their paper and said, well, wait a minute, what about all that chlorine we're putting up in Earth's stratosphere? Uh-oh. And, put two and two together. At any rate, we realized we were harming the ozone layer with these chlorofluorocarbons. And you can see throughout the 1980s, the ozone hole deepens. And then it starts to level off and decrease. So this is an example of an inadvertent catastrophe, but it's also an example I will submit to you of what I call planetary changes of the fourth kind, which are intentional changes. Because what happened with the ozone hole, the problem with the ozone layers, we realized what we were doing, had global conversations about it. These conversations were fraught. There were people that said it was a hoax, and people that were trying to defend their profitability and all that. A lot of the same dynamics we see playing out now with carbon, and yet ultimately it became obvious what was happening, and global agreements were made, and it's been successful. The ozone hole is on its way to being fixed now. It's not fixed because it takes about 50 years to come back, even in the best case scenario, but it's on track. And this is an example, I think, an important proof of concept that we have it within us to respond in a different way to a global threat. It doesn't mean it's going to be easy or that it's inevitable that we'll succeed, but at least it's a proof of concept that we can perceive a global threat and act collectively, globally, to solve it. Some other examples of intentional planetary changes, in addition to ozone, of course, the really important one now is that changing our energy systems to ones that do not destroy the natural systems we depend upon. And that change is underway. It's going far too slowly now, which is leading to some great risk. But there's no question that this is an issue that's come to the world's attention and is in a painfully slow way being addressed now. Looking into the farther future, I mentioned before, especially in the introduction about Eugene Shoemaker, the problem of potentially threatening asteroids hitting the Earth. Well, this isn't something you need to lose sleep over tonight, but if we're going to start thinking of ourselves as a geological process, and I think we really don't have a choice, but we have to start thinking of ourselves that way, then we also have to start thinking of ourselves on longer time scales. Think of multi-generational projects that we can undertake. And the fact that we can perceive of the asteroid threat gives us actually not just an opportunity, but an obligation to solve it. And the good news is that we're observing these objects, and we're finding them, and there are mechanisms by which we think we probably would be able to divert the orbit of one of these objects. And so it may be that we're crossing this transition that's planetologically significant to a time when, to the boundary between when this was a threat to life on Earth and when it will no longer be a threat to life on Earth. That's one way of looking at one ramification of the time we're living in. Even on longer time scales, there's the possibility of dangerous natural climate change. We have this illusion that left to itself, if we just take our hands off, the Earth will be this paradise and climate will be fine. But that is an illusion because we've lived in this 10,000-year period of relatively steady and warm climate. Over longer time scales, the Earth goes through drastic fluctuations in climate, and we don't want to live through another ice age. Our civilization would not survive that. I don't think we would have to. I think if we're around for 50,000 years more, we will know enough to be able to prevent that from happening. To me, this is all sort of a spectrum of thinking on longer and longer time scales and starting to see ourselves as having agency, first fixing some of these self-imposed problems, but then in the long run being sort of guardians of Earth's biosphere, applying that knowledge we have. If we can see these problems coming, then I think we have no choice but to imagine how we would solve them. So, and this is just some cool data from the California Academy of Sciences. Each one of these is a real orbit of a known Earth-crossing object. And by the way, this is drastically sped up. So you don't have to, it's not as bad as it looks because you're seeing thousands of years go by now. But this is all by way of saying this is not a fiction. This is a real phenomena, but we've been cataloging these objects, and there's every reason to believe that we would see one many years out, and we would be able to do something about it. That's a longer topic, but that's my summary of it. Let me just check the time here. Oh yeah, I don't have that much more. Let me briefly. People talk about the Anthropocene. One of the arguments is, when did it begin? And that's kind of an interesting topic. You know, did it begin with the Industrial Revolution, or some people like using the atomic test horizon because there's a neat isotopic horizon. It's an interesting argument. But to me, the more interesting question is, when will it end, or will it end, or what will it be in Earth history? Will it simply be an event, a thin layer, like that boundary where that asteroid hit and killed the dinosaurs? Will it be an epoch, something more lasting, tens of millions of years? Or is it possible that it will be a planetary transition, the beginning of a new eon? And this is another way of asking, is our type of intelligence adaptive or self-limiting? And this leads to some interesting questions of SETI, the search for extraterrestrial intelligence, because when we talk about SETI, we always end up talking about longevity of civilizations. It turns out that's the key to, if you do the math of SETI, it turns out the key to whether or not there's anyone else to talk to, whether or not we can have the hope of sending or receiving a message and actually being able to have a conversation with somebody that's close enough so that at the speed of light, it's not impossible to have some knowledge of each other. It all depends on longevity of civilization. And when you realize that, you realize that the fundamental problem of humanity in the Anthropocene is the same as the fundamental problem of SETI. It's the question of whether or not a planet, a civilization with world-changing technology can develop a comfortable long-term relationship with that technology such that it becomes an agent of survival rather than an agent of destruction. So in my view, it is possible that, that we could achieve such a state and enter into a Sapienzoic. But in order to do that, we would have to become a new kind of entity on this planet and learn to live comfortably over the long haul with world-changing technology. Now, when I say this, people sometimes think I'm being ridiculously utopian to imagine that such a thing is even possible, looking at our world situation. They say, well, what about human nature? But in answer to that, I would say, think about the people of Pinnacle Point. Pinnacle Point is a site, an archaeological site near the southern tip of South Africa. And the seminal work on this site was actually done by a team from here at ASU, led by Curtis Marion. And this is the place where many people now think, many scholars now think, maybe the origin of modern humanity, the origin of anatomically modern humans. And this is a place where humanity seems to have retreated to when we almost went extinct. About 180,000 years ago, there was a genetic bottleneck. We were down to less than 1,000 individuals. This, by the way, is why there's so little genetic diversity, why all human beings are the same genetically, much more so than other large mammals. And this was because there was climate change in Africa. We were hunter-gatherers, but Africa was covered up by an ice age. The game died out. We couldn't hunt. We had to find a new way to live. A band of humans retreated to Pinnacle Point and figured out how to live off the ocean using shellfish and other fruits from the ocean. And in order to do this, they had to develop new kinds of technology. And in order to do that, they had to develop more sophisticated language. This is the first site where we see evidence of what's called long-chain complex recipe technology. In other words, technology, things like heat-treated rocks, where it's not obvious that how the products result from the initial ingredients, where there's some complex recipe that has to be taught from generation to generation. So this required an enlarged circle of cooperation and intergenerational cooperation. The use of sophisticated language to pass down this knowledge. So in the face of extinction, we reinvented ourselves. And this, I think, is one of the fundamental qualities of humanity, this capacity for reinvention when needed. And this gives me hope, because I think that's what we really do need to do now, is incorporate this knowledge of our planetary nature and really reinvent ourselves. And I would submit that this actually is something that is happening, although it's happening so slowly that we may not fully be aware of it. But when people tell me they think that Terra Sapiens is impossible, one thing I think of is, can you imagine talking to the people of Pinnacle Point and trying to describe to them a modern city the way we live now? It would just be impossible. They couldn't comprehend it. And maybe that's as hard for us as it is for us to comprehend the world of Terra Sapiens. And another thing to remember is that when we first lived in cities, they were horrible places. They were public health disasters. And we had to come up with new inventions that allowed us to live in that kind of density. And one of the best inventions were sewer systems that we don't even think of now because they're designed to be hidden from us. But that's what allows us to, before that we threw our crap in the streets. Now we have sewer systems. So that's what allowed us to live in such large numbers. And in a sense, our challenge now is to develop the sewer systems of the 21st century and do something about this effluence we're putting into the atmosphere. I'm kind of out of time, but this is just a point about the metaphors we use to describe ourselves. We're often talking about ourselves as a cancer or metaphors of criminality. And you can obviously see the applicability, but one of the insights that I feel I gained from thinking of humans as a geological force and thinking of ourselves in deep time is a little bit of sympathy for the human race, that we're in this jam, yes, of our own making, but that we've sort of stumbled into a trap. And that it doesn't mean that we're evil, it just means that we're confused. And I think that it's a trap to think of ourselves as merely a virus, because viruses don't get together and talk about it and say, hey, maybe we shouldn't be a virus. There's something else going on here. So there's metaphors of the unschooled driver, where we realize we're driving this big rig down the highway and everything we love is in the back, but oh, I don't know how to drive. I better figure it out in a hurry. The metaphor of the sleepwalker, that in a way we're sort of waking up to find ourselves in the middle of committing these crimes that we stumbled into, and we don't. We have no choice but to sort of grow up now. The metaphors of maturity. I just think there are different ways we can describe ourselves where we don't have to get so down on ourselves, but can try to reach for our potential for reinvention and embrace the challenges of the 21st century. Okay, in closing, this is a cartoon you may have seen by the great underground cartoonist R. Crumb, where he portrayed a random place in America once every decade throughout the 20th century. So you start off, it's this pastoral scene, and then there's still pretty pastoral, but there's a train, and then there's a telegraph line. And then by the time you get down to the bottom right, you're in this modern, Anthropocene urban blight situation. And he asked, what next? And then the Stuart Brand, who edited the journal Coevolution Quarterly that he drew this for, asked him about 20 years later if he would draw an epilogue to this. And he said, okay, I will, but I'm going to draw 3. And these are the 3 that he drew. The top one is he called worst case scenario, ecological disaster. And you can see what that looks like, no fun. The second one he called the fun future, techno-fix on the march. And everything is solved by these high-tech inventions. And there is nature, but it's very regulated, and flying cars, and gee whiz, that's fun. And the third is the ecotopian solution, where everything has gone back to low-tech, when it's, sort of looks like Northern California in the 70s, but everybody's living in tree houses and riding bicycles and in fruit stands and playing acoustic instruments. And I would submit that in order to avoid ecological disaster, the top one, we're going to have to do some smart combination of 2 and 3. Some combination, we can't just innovate our way out of all problems, but we can't solve everything through restraint either. We've got to use our ingenuity and recognize limits. And some combination of ingenuity and restraint is going to be what gets us through this Anthropocene bottleneck. So in conclusion, I'll just quote one of my heroes, Dr. Martin Luther King, who said that if we are to have peace on Earth, which I also interpret to mean if we're going to build a sustainable civilization, then our loyalties must transcend our differences. And this means we must develop a world perspective. So I'll stop there. Thank you very much.
Well, David, that's plenty of food for thought. And as we mentioned earlier, there will be a symposium tomorrow developing this theme broadening it and discussing not just the technological but the philosophical implications of possible futures and the emergence of planetary intelligence. And that symposium is co-sponsored by ASU's Interplanetary Initiative. And the co-chair of that initiative is with us tonight, Lindy Elkins-Tanton, who is also director of the School of Earth and Space Exploration, and has the wonderful job as well of being principal investigator of the forthcoming Psyche mission. Among all those many things flying around on the screen there is a very extraordinary, indeed possibly unique asteroid, which is totally metallic. And she's going to, metaphorically speaking, take humanity there. And I'd like to ask her to come forward with a little gift of appreciation for your lecture. So, Lindy, over to you. If you want to say a few words, you don't have to, but if you wish to, there's the mic.
Thank you so much. This is really lovely for me because David and I have been friends for years, and we've been through the Venus Wars together, and they're not finished. We're going back to Venus. We are. I'm just going to say that right now. And I really admire his work, and I lived in Washington while he was working at the Library of Congress, and indeed, you were the first person to take me through the Library of Congress, and because of you, I'm a proud owner of a Library of Congress card. And so I just want to say briefly that I'm really thrilled, actually, that Paul and Sarah Walker invited Interplanetary Initiative to co-sponsor this event, because indeed what you're talking about is exactly what this initiative is about. It's about the fact that as humans, we have the ability to come together and make something better. We have this remarkable ability to have joy and optimism and agency and to envision our future and to create it the way we want. And that is what we're working on in Interplanetary Initiative, and I'm so pleased to know that David is walking around this Earth and telling everyone that they can feel that way. And so because of Paul and Sarah's excellent work, I had nothing to do with this lovely award that I'm allowed to give you, but I'm not going to give it to you yet, so don't reach out for it. I just want everyone to, if you can see at all what this is actually a piece of Sahara Desert glass. When a meteoroid hit in the desert, is it from Libya? Is it a Libyan glass piece? And many would know. It actually fused the sand of the desert into glass. And so it's just a gorgeous summary of all you've said, and so grateful that you could be here with us tonight.
Wow.
David, thank you so much.
Thank you very much. Yeah, thank you.
Well, we have a little while for questions, and then there's book signing afterwards. Would you like me to moderate the questions, or
Sure.
would you? Yes, let me do that. The acoustics in this auditorium are pretty good, so we're not going to pass around the microphone, but I will repeat any questions just for clarity. So, are there any? I don't see a single hand. Well, we have a gentleman. There's a lady right at the back. Let's take that one first, and then this gentleman here. Yes. Just shout. How long would it take to do the Venus
Rant.
Oh, yeah, please,
I'll do
no
the-
more than 30 seconds.
I'll do the 20-second version of it. Venus is, in many ways, a twin planet to Earth. It's the same size, born out of very similar conditions. And it's a hard place to explore because it's covered in clouds, and the surface conditions are intense. It's 900 degrees Fahrenheit there. So it's not an easy place to land. It's not an easy place even to observe from orbit. So partly as a consequence, we've neglected it and gone and studied some easier places. But if we want to really understand how Earth fits in with other planets, and even understand our climate in a lot of ways, and understand the paths of life and how a planet can go from being habitable to perhaps uninhabitable, then it's absolutely essential that we send more missions to Venus.
But there could be life in the clouds.
That's right. I didn't even get to that, because that would have been the 30-second version.
Right. So we shall see. Yes, go ahead.
Well, yeah, it may. First of all, we're not going to burn the rest of those fossil fuels. We can't. And in fact, even though, as I said, we're not making the transition quickly enough, if you look at the, solar energy is getting cheaper and cheaper, wind energy is getting cheaper and cheaper. The curves are going in the right direction. They just need to go more steeply. But as far as population, that is a concern, but there's good news there too. In a cautious way, all of the projections show population peaking and then leveling off later this century. And now peaking at maybe 10 billion people, and that's a scary thought because we're pushing the carrying capacity, but it levels off, and it levels off for the right reasons. Not because the death rate increases, but because the birth rate decreases. And that's happening largely because of the decrease in extreme poverty, and in particular, when you educate girls and women in poor countries, the family sizes decrease, and people have better quality of life that doesn't require them to sort of feel like they have to have really large families just for survival. And that is happening. There's some, it's complex. There's some geographical pockets in sub-Saharan Africa where it's going to be very challenging. But the overall global trend is towards a leveling off of population for the right reasons. So we can envision 100 years from now a time when population is stabilized and we are no longer using fossil fuels. I think that time will come, and we'll look back on this time and we'll think, wow, why did we do that for so long? That was really foolish. Sort of the way we look at whale oil now. We used to power ourselves with whale oil, and we got off that, but we did it a little too long, and we did damage. And I think that's going to be the situation now. And we'll look back, and we'll probably be in the process of repairing that damage in 100 years.
We just got our Tesla car, so we're doing our bit. Gentleman in blue. How long have we got? Right.
Is that a yes/no question? could you? No. I mean, that's a really vexed question, there's some paradoxes there because, in a way, we'll be able to answer that question better once we find life elsewhere. But in order to search for it, we have to have some provisional definition. So we often talk about self-sustaining chemical processes that evolve through Darwinian selection, that kind of thing. Yes.
So I guess everyone heard that. What is the force? That's
Well,
that is driving this emergence of life.
The force is
it's a provocative word.
Is the search for chemicals for equilibrium. So you have chemicals that are out of equilibrium, meaning that that if they can react with each other, they can find some lower energy state. And if I had to say what the force was, it's chemicals seeking combination, which chemicals do for reasons which, if we really want to know why, we'd have to appeal to our physicist friends here. But
yes, we know all about this stuff.
Yes. But ultimately, it's chemicals reacting according to the laws of chemical thermodynamics that we've been able to discern, and it seems to be, as near as we can tell, a natural consequence of certain environments that form early in planetary evolution.
Well, actually, we don't have a clue.
Well, I said as near as we can tell, but that's not very near.
It's still wide open.
That's right.
Yes. Flat Earth, yes.
Oh, man.
Yeah, what about the flat Earth? What is the evidence for the flat Earth?
What's the quote? Against stupidity, the gods themselves contend in vain. But more seriously, I don't really know. I suspect there isn't a huge resurgence in that. I've been wondering about this. I know you see people online arguing about this, and there's some celebrities that have made a big deal of being obstinately in favor of the flat Earth. And of course, the general problem of irrational beliefs that fly in the face of what we know scientifically is a real problem that we have to sort of, that's, the answer to that is education, and we're all hopefully doing our part there. But I'm not totally convinced that there's a massive scourge of people who believe in the flat Earth. I feel like that's maybe just an internet meme.
Yeah, I haven't actually come across anybody at this stage. I think we're just going to have two more questions, and they're both in the middle there. So there's a lady behind you, sir. So is it a lady? No, I'm sorry, I can't see from here. It's not.
Well, there's a couple different ways in which we could address that, because in some sense it is a naturalistic process, because human beings are products of biological evolution, and maybe there's a philosophical sense in which you can say everything that we do is, quote, natural, and you can start to pick at that distinction between natural and artificial. But I don't think that's really what you mean. I think that actually, if they were smart alien astrobiologists, and I assume they are, because if they've made it all the way here and they've been observing us in such a fashion, they got to be pretty good at what they do. Then they would notice there are some definite differences between the climate change occurring now and historical climate change. It's true that the carbon dioxide levels have been much higher in the past, at times in the distant past, than they are now. But the rate of change, combined with the rate of change in so many other Earth qualities, and I showed you that one chart near the beginning where all these things are changing at the same time. So I think a careful observer of the Earth with that kind of time perspective would notice that this is actually quite different from any of those changes that have occurred in the past.
Okay, and we'll take the last question from the gentleman in the stripy top. Oh, all right, we'll come back to you in a moment.
Why does it seem so difficult to find evidence of life on Mars? Well, maybe because there isn't life on Mars. And if there is, it's certainly not lying around on the surface injecting massive quantities of oxygen into the atmosphere as life is on Earth. It's cryptic, hidden. So either there's no life on Mars or it's deep underground and in places that we haven't been able to search yet.
Right. So, and yes, but that definitely the final one. You, sir.
Yeah. So, yeah, there's a whole literature of people sort of arguing constructively over when it began. And there's the idea that I mentioned when we first, the invention of the steam engine, and where we started burning fossil fuels and injecting CO2. There's the idea of the nuclear bomb threshold. There's this other school of thought of what's called the early or Paleo-Anthropocene, where in fact, if you look about 7,000 years ago, you can see the first evidence of climate change caused by widespread human activities of clearing fields for agriculture and so forth. So there is actually a definite climate imprint about 7,000 years ago. I think all of these are interesting. Actually, I have a pet hypothesis that I've published and has been mostly ignored, which is fine, but I'll stick to it because I like it, which is that, so people talk about looking for finding the golden spike, which is a particular geological strata. A lot of these transitions in the geologic timescale, there's actually a particular strata that's sort of the type strata that's emblematic of that transition, and that some of them there's literally a golden spike in the ground somewhere, but that's the phrase. My idea is that the typical strata that represents best the Anthropocene, and therefore is where the golden spike should be, is Tranquility Base on the moon. Because that is a geological formation where those boot prints are that could have not been formed by any other species without the kind of capabilities that we have. So that's, I put my hat in the ring and suggested that, but so far it hasn't been widely embraced by the geological community.
Well, I like it. Anyway, so it just remains for me to thank you very much once again, David. And go outside and take up station behind your books, and everyone is welcome to go and buy a copy. I don't think there's enough for everyone here, though. Thank you.